Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle. Inside this quarter circle, we know that the radius of this small circle r equals to the square root of 2 units in its length, and our mission is to find out the area of this green shape. So first of all, we'll define the relevant points to this question with letters. We define this point as A, we define this point as B. This is the center of the quarter circle. We define the center of the quarter circle as O. We define this point as C. We define this point as D. This point is the touching point between the small circle and the big semicircle. We define the touching point, this touching point as E. And finally, we define this point that is the center of this small circle as F. In the next step, we'll join points F and C together by a straight line. Point F is the center of the small circle, point C is the point of the small circle itself, therefore line segment FC is the radius of this small circle that is equals to the square root of 2 units in its length according to what is given as the question. We can implement here rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have this circle and we have also this tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is equal to capital R. The radius OM is drawn to point M that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius FC is equal to R is equals to the square root of 2 units. The radius FC is drawn to point C that is the point of tendency of tangent OD with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FB that is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, in this small quadrilateral FBOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this missing fourth angle must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this small quadrangle FBOC to 360 degrees, the missing angle must be equal to 90 degrees in its size. So inside the small quadrangle FBOC, we have 4 right angles. Therefore, we know that any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So relate to this small quadrangle FBOC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle FBOC, side FB must be equal to the opposite side CO. But FB equals to the square root of 2 units, therefore CO must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, side BO must be equal side BO must be equal to the opposite side FC. So, but FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. So actually found out that this small quadrangle BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this quadrangle is equal to the square root of 2 units in its length, therefore it is a square. In the next step, we join points O and F together by a straight line. By joining points O and F, we create the right triangle OBF. In the right triangle OBF, side OB equals to side BF. They are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle OBF, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle OBF? We have here this angle is equal to 90 degrees. This angle is alpha, this angle is alpha, so it is 90 degrees plus 2 alpha. In total, the sum of angles must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So here we divide this equation by 2, and finally we get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So actually, this is angle alpha. This is equals to 45 degrees in its size. And this is also angle alpha. This is equals to 45 degrees. We will continue to focus on this right triangle OBF. We will implement the Pythagoras theorem in this small right triangle OBF. So, in this small right triangle OBF, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle OBF is OF, therefore the square of the hypotenuse is OF square. And it must be equal to BF square. plus b all square. Repeat again according to the Pythagoras theorem. In the right triangle of BF, OF square equals to BF square plus BO square. So OF square, that is the square of the hypotenuse, equals to BF square. BF is square root of 2, therefore BF square is square root of 2 squared, that is 2, plus BO square. BO is also square root of 2, therefore BO square is square root of 2 squared, that is 2. So in conclusion, found out that OF square equals to 2 plus 2, that is 4. OF square equals to 4. Here we take a root out of this equation, and finally we get that the length of the hypotenuse OF is equals to the square root of 4, that is 2. So here the length of OF it is equals to 2 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass for their touching point. In the drawing we have two circles. The small circle is located inside the big circle and they touch each other here at point P. Therefore we have here an internal match between those two circles, that is to say they are touching each other internally at point P. So here, according to this rule, rule 9, the straight line that connects their centers together, the center of the big circle is here at point O, the center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. This straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. So whenever you have an internal match between two circles, you can implement rule 9 in the dead circles, those circles. Okay? So we can actually implement rule 9 in our drawing. Why? Because in our drawing, first of all, this small circle is located inside the big quarter circle, and those two circles that touch each other internally here at point E. Therefore, we can implement here rule 9. According to rule 9, the straight line that connects their centers together, the straight line that connects their centers together, point O is the center of the big quarter circle. Point F is the center of this small circle. And the straight line that connects their centers together is the straight line OF. This straight line OF must pass through point E, that is their touching point. The straight line OF must pass through point E. Or OFE is one straight line. OFE is one straight line. So we will extend the straight line OF, and according to rule 9, the straight line OF must pass through point E. Or OFE is one straight line. OFE is one straight line. So I write it down here. That according to rule 9, OFE, line segment OFE is one straight line. But what is the other definition of the straight line OFE. Actually, the straight line OFE starts from point O, that is the center of the big circle, and ends at point E, that is the point on the big circle itself. This is exactly the definition of a radius. Therefore, OFE is the radius of the big circle. We define the radius of the big circle as capital R. So I write it here that capital R is the radius of the big circle. So capital R equals to OFE. What is the length of OFE? First of all, here we have point F, that is the center of the small circle, and point E is the point of the small circle itself. Therefore, FE is the radius of the small circle, that is equals to the square root of 2 units according to what is given as the question. So OFE, because of the fact that OFE is one straight line, it means that OFE in total will be equal to OF plus FE. OF equals to OF plus FE, because it is one straight line. So OF equals to OF, that is 2, plus FE, that is square root of 2. So in conclusion, we found out that the radius of the big circle capital R equals to 2 plus square root of 2 units in its length. Okay. We define the intersection point between the straight line OFE and this small circle SH, this point SH. So we know that OFE is one straight line, therefore edge FE is also one straight line, because edge FE is part of OFE. Therefore edge FE is also one straight line, but edge FE is one straight line that touches this small circle here at point H and here at point E. Any straight line that touches the circle at 2 points is a chord. So edge FE is a chord of this small circle, but it is a special chord. It is a chord that passes from point F, that is the center of the small circle. We know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge FE is the diameter of the small circle, because it passes from point F, that is the center of the small circle. The diameter of the small circle. We also know that the diameter of any circle bisects the circle into 2 halves. Into 2 halves that equal to each other in their areas. So this is the first half, and this is the second half. So this is the first half of this small circle, and the first half, the half of a circle, is defined as a semicircle. Therefore this is a semicircle. So we found out that this shape is a semicircle. It is actually half in its area. It is half of the area of the small circle, because therefore it is a semicircle. Okay. In the next step, I present to you a new notion. It's actually sector. What is a sector? We have here a circle and we have the green shape AOB. The green shape AOB is a sector. A sector is part of a circle. Okay, here we have the circle and AOB is part of this circle. If we look at this circle as a cake, then AOB is a slice of this cake. One slice of this cake, AOB, is a sector. And the green sector AOB consists of two legs. The first leg is AO and the second leg is BO. Both legs, they are the radii of this circle that is equal to R. And the angle between the two legs AO and BO of this sector AOB is angle theta. So what is the area of this green sector AOB? The area of this green sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. So in conclusion, found out that the area of a sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Okay. Our mission is to find out the area of this green shape. So what is the area of the green shape? For the drawing, it is very easy to see that the area of this green shape is equal to the area of the big sector AOE. The big sector AOE is part of the big circle. So it is the area of the big sector AOE here. The line, the rounded line above AOE is the sign for the area, for the sector. This is the area of sector AOE, and the square brackets is the sign for the area. So in total, this expression means that the area of sector AOE minus the area of this small semicircle minus the area of the small semicircle. The semicircle is half of the area of the small circle. Minus the area of this shape HBO. So minus the area of the orange shape HBO. Minus the area of the orange shape HBO. I repeat again, the area of the green shape in total equals to the area of the big sector AOE minus the area of the small semicircle minus the area of this orange shape HBO. The area of the green shape equals to the area of sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. So first of all, we find out the area of the big sector AOE. Again, the big sector AOE is part of the big circle. The big circle, the radius of the big circle is equals to capital R, and therefore the area of the big circle equals to pi times capital R squared. Therefore the area of the big sector AO equals to the area of the circle that contains the sector, that's actually the area of the big circle, that is pi times capital R squared, times the angle between the legs of sector AOE. This is sector AOE. One leg is AO and the second leg of sector AOE is EO. Those are the two legs, and this is the angle between the legs of this sector. And we already found out that this angle equals to 45 degrees in its side. So it is times 45 degrees over 360 degrees. So the area of the big sector AO equals to pi R squared. So it is pi capital R equals to 2 plus square root of 2, therefore capital R squared equals to 2 plus square root of 2 squared. And here we have 45 degrees over 360 degrees, it is 1/8 or 1/8. So we have to divide the area by 8. So this expression equals to pi, and 2 plus square root of 2 squared equals to, according to the algebraic identity, that a plus b squared equals to a squared plus b squared plus 2 times ab. 2 plus square root of 2 squared equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2 times square root of 2 divided by 8. So the area of the big sector AOE total will be equal to pi. Inside the brackets we have 4 plus 2, that is 6, plus 2 times 2, that is 4. So in total this expression equals to 4 times square root of 2 divided by 8. Here we will divide both the numerator and the denominator of this expression by 2. And we get that it will be equal to pi. Inside the brackets we have 6. 6 over 2 is 3. Plus 4 times square root of 2 over 2 is 2 times square root of 2. Divided, we have to divide the denominator 8 also by 2. 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. So write it down here. The area of the big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units. Okay. In the next step, we'll find out the area of the small semicircle. What is the area of this small semicircle? The area of any semicircle equals to the area of the circle over 2. So it is the area of this small circle, that is pi r squared, pi small r squared over 2. Capital R is the area of the big circle. So the area of the small semicircle equals to pi r equals to the square root of 2 units according to what is given as the equation. Therefore, r squared is square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so left only with pi. In conclusion, we found out that the area of the small semicircle in total it is equals to pi square units. Finally, we have to find out the area of this orange shape HBO. What is the area of the orange shape HBO? From the drawing, it is very easy to see that the area of this orange shape HBO is equals to the area of the right triangle FBO minus the area of this small sector FBH. This small sector FBH is part of the small circle. Repeat again, the area of the orange sector HBO in total it is equals to the area of the right triangle FBO minus the area of the small sector FBH. What is the area of this triangle FBO? Actually, the area of any triangle equals to the base of the triangle times the height to the base over 2. In our triangle FBO, the height, the base and the height, they are both equal to the square root of 2 units in their lengths. So the base is square root of 2 and the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion, we found out that the area of the right triangle FBO is equals to 1 square unit. In the next step, we find out the area of the small sector FBH. I will remind you that the area of the small sector FBH is part of the small circle. So what is the area of the small sector FBH? The area of any sector is equals to the area of the circle that contains this sector. The small circle contains this sector FBH. Therefore, the area of the small circle is pi times r squared times the angle between the legs of the small sector FBH. This is the angle between the legs of sector FBH. This angle equals to 45 degrees. So it is 45 degrees over 360 degrees. What is the value of pi r squared? It is pi and r is square root of 2, therefore r squared is square root of 2 squared, that is 2. So in total, pi r squared, that is the area of the small circle, equals to 2 pi, times 45 degrees over 360 degrees, it is 1 over 8. So it is divided by 8. We have to divide the area of 2 pi of the small circle by 8. Here we divide both the numerator and the denominator of this expression by 2. this expression, 2 pi over 2 is pi and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector FBH is equals to pi over 4 square units. Therefore, in total, the area of the orange shape HBO it is equals to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4 square units. So in total, the area of the orange shape HBO equals to 1 minus pi over 4 square units. Again, our mission is to find out the area of this green shape. I repeat again, the area of the green shape equals to the area of the big sector AOE that we have already found out, minus the area of this small semicircle that we have already found out, minus the area of this orange shape HBO that we have already found out just right now. Repeat again, the area of the green shape, in total, the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HBO. We have already found out that the area of the big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small semicircle. We have already found out that the area of the small semicircle equals to pi square units minus the area of the small orange shape HBO. We just right now found out that the area of the small shape HBO equals to 1 minus pi over 4 square units. So in total, the value of this expression is the area of the green shape. So we simplify this expression in order to find out the area of the green shape in terms of numbers. Here we'll open the brackets and get that pi times 3 is 3 pi plus 2 times square root of 2 times pi over 4 minus pi, and we have minus before the brackets. We'll open the brackets here. After we will open the brackets, we will have here minus 1, and here we have minus times minus is plus, so it is plus pi over 4. So the area of the green shape in total equals to 3 pi plus 2 times square root of 2 times pi divided by 4. Here we have minus pi plus pi over 4 is minus 3/4 pi. Here we have minus 1. We will multiply minus 1 by 4, and then we divide it by 4 in order to have a common factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So in conclusion, we found out that here we have common factor of 4 in the denominator of those three expressions. So in total, the area of the green shape we have in the numerator 3 pi plus 2 times square root of 2 pi minus 3 pi minus 4, and in the denominator we have 4. So here we have 3 pi minus 3 pi is 0. After we cancel 3 pi, we left only with 2 times square root of 2 times pi minus 4 over 4. So here we divide both the numerator and the denominator of this expression by 2, and we get that 2 times square root of 2 pi over 2 is square root of 2 times pi, minus 4 over 2 is minus 2, divided, we have to divide the denominator of 4 also by 2, 4 over 2 is 2. So in conclusion, found out that the area of this green shape equals to either square root of pi minus 2 over 2 square units, or in terms of numbers, this expression equals to 1.2214 square units. Repeat again, the area of this green shape equals to the square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, so in the next step I will summarize the lecture. In this lecture we found out the area of this green shape. In the drawing we have a circle inside this quarter circle. In addition, we know that the radius of this small circle equals to the square root of 2 units in its length. Again, our mission is to find out the area of this green shape. So first of all, we defined the relevant points to this question with letters. We define this point as A, we define this point as B. This point is the center of the quarter circle, or the center of the big circle. We define the center of the big circle as O. We define this point as C, we define this point as D. This point is the touching point between this small semicircle, this small circle, and this quarter circle. We define the touching point between them as E. And finally, we define the center of this small circle as F. Then we join points F and C together by a straight line. What is the definition of line segment FC? Line segment FC starts from point F, that is the center of the small circle, and ends at point C, that is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, line segment FC is the radius of this small circle, R, that is equals to the square root of 2 units according to what is given as the question. The radius FC is drawn to point C, that is the point of tendency or tangent OD with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FC the radius FB is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. Then we focus on this small quadrilateral BFOC. Inside this small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its side. Again, in order to complete the sum of the angles in this small quadrilateral FBOC to 360 degrees, the missing angle here must be equal to 90 degrees in its side. So, actually found out that inside quadrilateral BFOC we have 4 right angles. And we have the rule that any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BFOC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC in rectangle BFOC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, side FC must be equal to the opposite side BO. But FC equals to the square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So actually found out that quadrilateral BFOC is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this quadrilateral is equal to the square root of 2 units in its length. Therefore, quadrilateral BFOC is a square. Then we joined points F and O together by straight line, and we focused on the right triangle BOF. In the right triangle BOF, those two sides are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. Okay, so if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. And it's especially this true in the right triangle FBO. So which angles we have in the right triangle FBO? We have alpha plus alpha, that is 2 alpha plus 90 degrees. In total, they must be equal to 180 degrees according to the rule that I mentioned. We subtracted the 90 degrees from this equation and found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. Here we divided this equation by 2 and finally found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equal to 45 degrees in its size, and this is also angle alpha that is equal to 45 degrees in its size. Then we implemented on the same right triangle FBO the Pythagoras theorem in order to find out the length of the hypotenuse FO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle FBO is FO, therefore the square of the hypotenuse is FO square. That is must be equal to BF square plus BO square. Repeat again, in the right triangle OBF, according to the Pythagoras theorem, OF square equals to BF square plus BO square. OF square, that is the square of the hypotenuse, must be equal to BF square. BF is square root of 2, therefore BF square is square root of 2 square, that is 2, plus BO square. BO is square root of 2, therefore BO square is square root of 2 square, that is 2. So we found out that OF square, the square of the hypotenuse, equals to 2 plus 2, that is 4. So OF square equals to 4. We took out of this equation and finally found out that OF equals to the square root of 4, that is 2. So the length of the hypotenuse OF is 2 units. Then I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. In the drawing we have two circles. The small circle is located inside the big circle and they touch each other internally at point P. Therefore, we have here an internal notch between the two circles, and according to this whole line, the straight line that connects their centers together must pass through their touching point, that is point P. Here, the center of the big circle is here at point O, the center of this small circle is here at point M. The straight line that connects their centers together is the straight line OM. And according to this whole line, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. We can actually implement all 9 in our drawing. Why? Because in our drawing, first of all, in our drawing, we have an internal notch between the small circle and the big quarter circle. Why? Because the small circle is located inside the big quarter circle and they touch each other internally at point E. Therefore, we have here internal notch. For that reason, we can implement here rule 9. According to rule 9, the straight line that connects their centers together must pass through their touching point. The straight line of the big circle is here at point O. The straight line of the small circle is here at point F. The straight line that connects, again, the straight line, again, the center of this big circle is here at point O, and the center of this small circle is here at point F. And the straight line that connects their centers together is the straight line OF. And according to rule 9, the straight line OF must pass through point E, that is their touching point. Again, the straight line OF must pass through point E, that is their touching point, or OFE is one straight line. So we found out that OFE is one straight line according to rule 9. We know that OFE is straight line. What is the other definition of the straight line OFE? The straight line OFE is the radius of the big circle. Why? Because of the fact that the straight line OFE starts from point O, that is the center of the big circle, and ends at point E, that is the point on the big circle itself. This is exactly the definition of a radius. Therefore, OFE is the radius of the big circle. We define the radius of the big circle as capital R. Here, capital R is the radius of the big circle. So, capital R equals to OFE. And because of the fact that OFE is one straight line, it means that OFE, the length of OFE in total, it will be equal to OF plus FE. Again, R that is capital R that is equal to OFE equals to OF plus FE. OF is 2, and what is the length of FE? FE is the radius of the small circle that is equal to the square root of 2 units. Why? Because it starts from point F, that is the center of the small circle, and ends at point E, that is the point on the small circle itself. Therefore, FE is the radius of the small circle that is equal to the square root of 2 units in itself. Again, OF is 2 and FE is square root of 2. So in total, the radius of the big circle capital R equals to 2 plus square root of 2 units in its length. And we know that OFE is one straight line. We defined the intersection point between the straight line OFE and this small circle as H. If OFE is one straight line, it means that HFE, that is part of OFE, must be also a straight line. So we know that HFE is a straight line that touches the small circle here at point E and here at point H. Any straight line that touches the circle at 2 points must be a chord. So HFE is a chord of this small circle, but it is a special chord that passes from point F, that is the center of the small circle. And note that any chord that passes for the center of the circle must be the diameter of the circle. In conclusion, we found out that HFE is the diameter of the small circle because it passes from point F, that is the center of the small circle. So HFE is the diameter of the small circle, we know that any diameter of any circle bisects the circle into two equal areas. This is the first area and this is the second area. And those two areas, they are equal to each other. Each area is defined as a semicircle. So this is a semicircle and this is also a semicircle. So we found out that this shape, HBE, this shape is a semicircle. Okay? In the next step, I presented to you what is a sector. Here we have a circle and the green shape AOB is a sector. A sector is part of a circle. If we see this circle as a cake, then AOB is a slice, one slice of this cake. So a slice of a cake is this sector, sector AOB. Okay. Sector AOB consists of two legs. The first leg is AO and the second leg is BO. Both those two legs of sector AOB, they are the radii of this circle that is equal to R. And the angle between the two legs AO and BO of sector AOB is theta. And the area of this sector AOB equals to pi r squared, that is the area of this circle, times theta, that is the angle between the legs of the sector AOB, over 360 degrees. So the area of any sector equals to the area of the circle that contains the sector. In this case it is pi r squared, times the angle between the legs of this sector, that is theta, over 360 degrees. Okay? Repeat again that our mission is to find out the area of this green shape. What is the area of this green shape? From the drawings it's very easy to see that the area of this green shape in total equals to the area of the big sector AOE. The big sector is part of the big circle, of course, minus the area of this semicircle, the small semicircle. The small semicircle is half of the small circle in its size, minus the area of this orange shape, HBO. Again, the area of this green shape equals to the area of the big sector AOE, minus the area of this small semicircle, minus the area of this orange shape, HBO. The area of the green shape in total equals to the area of the big sector AOE, minus the area of the small semicircle, minus the area of the orange shape, HBO. What is the area of the big sector AOE? Repeat again that the big sector is part of the big circle. Therefore, the area of the sector will be equal to the area of the big circle, that is pi times capital R squared, times the angle between the legs of this sector AOE. This is the angle between the legs of sector AOE, that is equals to 45 degrees. So it is 45 degrees over 360 degrees. We have already found out that capital R equals to 2 plus square root of 2, therefore capital R squared equals to 2 plus square root of 2 squared. So pi r squared is pi times 2 plus square root of 2 squared times 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1 over 8, so we have to divide the area by 8. So what is the value of this expression? We have here pi and 2 plus square root of 2 squared equals to 2 squared, that is 2, plus square root of 2 squared, 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2, according to the algebraic identity, that a plus b squared equals to a squared plus b squared plus 2 times ab. And we have to divide it by 8. So here we have pi, inside the brackets we have 4 plus 2, that is 6, and 2 times 2 is 4. So in total this expression equals to 4 times square root of 2 divided by 8. Here we divided both the numerator and the denominator of this expression by 2. So we have here pi, and inside the brackets we have 6. 6 over 2 is 3, and we have here plus 4 times square root of 2. 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide the denominator 8 also by 2. 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. This is the expression of the area of the big sector AOE. We have to subtract from the area of the big sector AOE the area of the semicircle, the small semicircle. The area of this small semicircle. The area of a semicircle equals to the area of the circle over 2. The area of the small circle is pi r square, and when we divide the area of the small circle pi r square by 2, we get the area of the semicircle. So pi r square, we have r is square root of 2, therefore r square is square root of 2 square, that is 2. So in total the area of the small circle equals to 2 pi, and if we divide it by 2, we get the area of the small semicircle. 2 over 2 is 1, so we found out that in total the area of the small semicircle equals to pi square units. And finally we have to subtract also the area of the small shape HBO, the small orange shape HBO. What is the area of the orange shape HBO? From the domain it is very easy to see that the area of this orange shape HBO equals to the area of the right triangle POF minus the area of this small sector FBH. Again, the area of the right triangle FBO minus the area of this small sector FBH equals to the area of this orange shape BOH. Repeat again, the area of the orange shape HBO equals to the area of the right triangle FBO minus the area of the small sector FBH. The small sector FBH is part of the small circle, of course. So what is the area of the right triangle FBO? The area of the right triangle FBO equals to the area of any triangle equals to the base of the triangle times the height of the base over 2. In our specific case, the area of the right triangle FBO will be equal to FB equals to BO equals to the square root of 2 units. So the height equals to the base, they are both equal to the square root of 2 units. So the base is square root of 2, the height is also square root of 2 divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, we found out that the area of this right triangle FBO equals to 1 square units, and we have to subtract from the area of the right triangle FBO the area of this small sector FBH. The small sector FBH is part of the small circle, and therefore the area of the small sector FBH equals to the area of the circle that contains the small sector FBH. The small circle contains the small sector FBH. Therefore, the area of the small circle is pi r square times the angle between the legs of this small sector FBH, it is 45 degrees over 360 degrees. So it is pi r square times 45 degrees over 360 degrees. R equals to the square root of 2, therefore r square is square root of 2 squared, that is 2. So in total, the area of the small circle is 2 pi, and we have to multiply it by 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1 over 8, so we have to divide 2 pi by 8. Here we divided both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that in total the area of the small sector FBH equals to pi over 4 square units. So in total, the area of the orange shape HBO equals to the area of the right triangle FBH, that is 1, minus the area of the small sector FBH, that is pi over 4. So in total, the area of the orange sector of the orange shape HBO equals to 1 minus pi over 4 square units. I repeat again that our mission is to find out the area of this green shape. The area of this green shape equals to the area of the big sector AOE minus the area of the small semicircle, this small semicircle minus the area of this orange shape HBO. Repeat again, the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape HVO. We have already found out that the area of the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the semicircle that is equal to pi minus the area of the orange sector of the orange shape HVO that is 1 minus pi over 4 square units. So actually the value of this expression in total it is equals to the area of the green shape. We simplify this expression in order to find out the area of the green shape in terms of numbers. So we open the brackets here. Pi times 3 is 3 pi plus 2 times square root of 2 times pi over 4. We have here minus pi minus. We have minus before the brackets. We open the brackets here. After we open the brackets, we get here minus 1. And we have minus times minus is plus. So it is minus 1 plus pi over 4. Minus 1 plus pi over 4. So here we have 3 pi plus 2 times square root of 2 pi over 4. And we have here minus pi plus pi over 4 is minus 3/4 pi. And we have here minus 1. We multiply minus 1 by 4 and then we divide it by 4 in order to a common factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So this expression in total equals to 3 pi plus 2 times square root of 2 pi minus 3 pi minus 4, or we have 4 in all the three denominators of the three expressions. So we write here 4. The common factor is 4 in the denominator of those two expressions, of those three expressions. Here we have 3 pi minus 3 pi that is 0. After we cancel 3 pi, we left only with 2 times square root of 2 pi minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2. 2 times square root of 2 times pi over 2 is square root of 2 pi. Minus 4 over 2 is minus 4 over 2 is minus 2. And we have to divide the denominator 4 also by 2. 4 over 2 is 2. So we found out that the area of this green shape equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, thank you very much.